Good day. Today we continue our series on electricity in physics, and our topic for today is series and parallel circuits. Under this topic today we will be differentiating between series and parallel circuits with a view to stating the features of both circuits, and then we will also look at how we can calculate effective resistance when resistors are connected in series and when they are connected in parallel. A series circuit is one in which all the charges produced by the cell can only flow in the same direction. What this means is that in a series circuit, you do not have any junction. You do not have anywhere in that circuit where the current can split or where the charges can split. All the charges have to go in the same direction, in the same way, in the same through the same devices at the same time. There is no avenue. So in other words, in series circuits, you will find that all the components in that circuit are connected end to end. You will find the head of one component connected to the tail of the next, then the head of that one connected to the tail of the next, and on like that until you have something that forms like a closed loop. That is what a series circuit is. For parallel circuits, on the other hand, you will find a junction or more than one junction there, either one junction or more than one junction, so that some components in that circuit are connected shoulder to shoulder as against head to head that we had in the series connection. So here we have a shoulder to shoulder connection such that it is possible for current flowing to split up. If you look at the diagram you have on this slide, you will find that when the charges are released from the positive terminal of the battery, as it gets to the junction below the two coils, the current can split up so that some of the current can flow to the right while the others flow upwards like that. So in any circuits where you have such connection where it's possible for charges to split up so that at certain times in that circuit you have different currents flowing through different devices, then what you say for that kind of circuit is a parallel circuit. Now let's look at some of the characteristics of series and parallel circuits. Now in a series circuit, one thing that they all share is the voltage. So when you have components connected in series, the voltage that is powering that circuit has to be shared among those components. In other words, if you have maybe 3 lamps all connected in series to say a cell of 3 volts, each of those lamps will take a portion of the 3 volts that is supplied into that circuit. So not each of the lamps will not have the total 3 volts, rather they have to share. Just like what example, let's say you have 3 people trying to share money, say $10. So one person cannot get the entire $10 because you have to share it, and you probably are sharing based on who is older or who is younger. So also in a series connection, the voltage will be shared based on which one has a larger resistance or which one has a lower resistance. So the one with the larger resistance will take the lion's share of the voltage, while the one with the lowest resistance will take the lowest share of the voltage. Also in series circuits, one switch can control all the components because all the charges flow through all the components at the same time. So once you put a switch somewhere to break up the circuit, then what you can have is a switch controlling all the components at a time. So one switch can control all components in a series circuit. One other thing that components in series circuits have in common is the current. The same current flows through all the components in a series circuit. Remember, we already said that they share the voltage, so they have different voltages, but they all have the same current. So if you have a lamp, a resistor, and an inductor connected in series, if the resistor has a current of 10 amps, the lamp will also have the same 10 amps and the inductor will have 10 amps as well, because like we said, all the charges flow together through the same points at the same time in the series circuit. Therefore, in a series circuit, if one of the components in series should break, if there should be a cut, a gap in that circuit, all the other components will go off. So that is one major disadvantage of a series circuit, because a break or a cut or a blowout of any component in series will mean that all the other components in that circuit will also not work. For a parallel circuit, however, you can place switches in different places so that you can use one switch to control, say, a lamp, and then another switch to control, say, an inductor or a TV, as it were. So that in this case now, the fact that you have switched off your lamp does not mean that your TV cannot work. Each of the components in the series circuit can be in a parallel circuit, can be controlled independently. But in a series circuit, the components has to be controlled at the same time together. Also, in a parallel circuit, the voltage across each component is the same as the voltage of the battery. So going back to the analogy of the 3 lamps I used, if you have 3 lamps connected but in parallel now, and it's connected to a 3-volt battery, lamp 1 would also have a voltage of 3-volt battery across it, while lamp 2 will have the same 3-volt battery, and lamp 3 will have the same 3-volt battery. So in this case, the voltage is the same. That's the difference between the parallel circuit and the series circuit. In the series circuit, voltage across all the circuits, all the components in a circuit is different. But in a parallel circuit, all the components in parallel have the same voltage. They don't share. Each of them grabs the full voltage. What this means then is that when you add more devices to a parallel connection, they will all stay bright. But if it was in series circuit, when you add more bulbs or more lamps to a series circuit, each bulb will get dimmer, because remember that in series circuit they are sharing the voltage. But in parallel circuits, each component still has access to the full voltage supplied by the battery in the circuit. So in parallel circuits also, if one component breaks, all the other components will continue to work. An example of this is what we see in our buildings, in our homes, schools, religious houses. You will find that the fact that a lamp is switched on does not mean that the TV will not work. The TV will work. The AC will work, even though you have switched off the fridge, for instance. So in this case, each of these components has its own switch, has its own control. So in this case, what we have is a parallel connection. So buildings are wired in parallel connections so that each component can work independently. But on the other hand, we have scenarios where the connections are done in series. For instance, your decorative lights, all the lights that shine, all the neon lights that shine at festive seasons, you'll find that the lamps will all come up once just one switch is turned on, so that you can use just one switch to turn on all the lamps or to turn all the lamps off. Having looked at what series and parallel connection is, let's look at how this applies to connection of resistors. Like I said earlier, whenever you have components connected end to end, one end to another end, what you have is a series connection. You pick the resistors on your slide, for instance. The 3 resistors are connected end to end so that it forms one straight line of connection. All currents flowing through the circuits will pass through all the resistors at the same time. All of them, there will be no split. That's a series connection of resistors. Now, if you want to find the total resistance in a kind of connection like this, where resistors are connected in series, you just need to do your arithmetic addition, your scalar addition. You just add up resistance 1 plus resistance 2 and resistance 3. Even if you have 10 resistances there, you just have to add them all up and you get your total value for the equivalent resistance in that connection. For a parallel circuit, as we looked at earlier, you have a shoulder-to-shoulder connection. So the resistors connected in parallel are connected shoulder to shoulder, like side to side. They are placed side by side, not head to head, but side by side. So in this case now, what you have is that current that flows into the circuit can split up. Some can go straight on to the resistance in the middle, while some will flow upwards to the resistance on top, and some will flow downward to the resistance below. And they all will now come out on the other side to join together. So through the three resistances, you have different currents flowing through them. This is a parallel connection of resistors. And in this case also, what you can simply do to find the total resistance is to add up the reciprocals of each resistance value for each resistor. What I mean by adding up reciprocals is, if the resistors have values 2 ohms, 3 ohms, and 4 ohms, you don't just add 2, 3, and 4. That's what you do for series. But now in parallel, you add up the reciprocal. That's 1 over 2 plus 1 over 3 plus 1 over 4. And you do LCM to get your answer. Now the answer that you get is 1 over the total resistance. So let's say you get 10 over 3. 10 over 3 is 1 over R. So to get the total resistance, you must again do the reciprocal. You must flip it back. Remember that when you were adding, you had already flipped the resistances to add. So when you want to get the total resistance, you must remember to flip your answer back to find the reciprocal of 1 over R. That is what will give you the total resistance in a parallel circuit. Here we have examples to look at. The first one has to do with a series connection of resistors. We have 3 resistors of resistances 1 ohm, 2 ohm, and 4 ohm connected in series. The equivalent is just the addition, as I said earlier, 1 plus 2 plus 4. That will give us 7 ohms. But for the parallel connection, 2 ohms, 3 ohms, and 5 ohms connected in parallel, we must add up their reciprocals. So that's why we have 1 over 2 plus 1 over 3 plus 1 over 5. And then we find the LCM. LCM is 30. If you do your LCM addition well, you will get your 1 over R to be 31 over 30. 1 over R will be 31 over 30. But don't forget that 31 over 30 is not the total resistance. It is the reciprocal of the total resistance. So to now find total resistance, you must flip it back again. So you must have the reciprocal of 31 over 30, and that is 30 over 31. That is what will now give you the total resistance value. Always note, again, when solving for parallel connection, use your LCM. But note that the subject of the formula in your parallel addition is 1 over R. So you must find the reciprocal of that to get your correct answer back. Thank you for today's lesson. I believe that this lesson has enlightened you a bit in being able to solve calculations in series and parallel circuits. Just for you to make attempts on, I put some questions here for you to try. So see and this, practice with them. Let me quickly explain something in the third question here. The third question, we have the 3 ohms and the 2 ohms in series, but 5 ohms and 10 ohms are in parallel. But 5 ohms and 10 ohms together, both of them, if you take both 5 ohms and 10 ohms as just one, if you take it as just one resistor, that one resistor will be in series with 3 ohms and 2 ohms. So what you need to do in number 3 is to first of all find the parallel connection of 5 ohms and 10 ohms in total. What will be the total of 5 ohms and 10 ohms in parallel? You do that. What you get is now in series with 2 ohms and 3 ohms. So you now add what you get to the 2 ohms and the 3 ohms. With that, you'll be able to find the equivalent resistance of that combination. Thank you once again for a nice class.